Hello there, Mr. Sutton here, bringing you the Algebra 2 3-2 lesson on complex numbers. This is going to be a two-parter. In this one, for part 1, we're going to be defining the imaginary unit I and using it to rewrite square roots of negative numbers. And we'll also use this to find complex solutions of quadratic equations and complex zeros. In part 2, we will be adding, subtracting, and multiplying these complex numbers. So what is this whole imaginary complex thing? Let's dive into it. So in the last lesson, when we were solving some quadratic equations, occasionally we ran into a situation where we had to take the square root of a negative number. And we threw up our hands and said, hey, no real solution, because you can't multiply any number by itself to get a negative, so you couldn't take the square root of a negative. But what if we could? What if we let I, we'll just make up a letter here, let's let I equal the square root of negative 1. Now, granting that the square root of negative 1 does not exist numerically, we can't graph it on the number line, what if we still allow this to be a thing? Then we could build a new branch of numbers called the imaginary numbers, right? Because this is just made up. So those would be like I, 2i, 3i. You could even have decimals and negative numbers, so like negative 7.1i and everything in between, maybe even some radicals. Just a whole new set of numbers with an I next to everything. We can actually expand this into something larger. So they've actually done this. I'm not making this up. A bunch of mathematicians made this up, and now it's a thing. Let's say that we take these imaginary numbers and put them together with some real numbers. This forms an even larger number set called the complex numbers. These are numbers that are in the form of a plus bi, where a is just some real number like a 4 or a 7, and bi is an imaginary number like one of these here, like a 2i or a 3i. Now this complex number set actually includes real numbers, because if you let this b value be 0, then this imaginary piece just kind of becomes invisible and you just have the real part. It also includes what I would like to call the pure imaginary numbers, because if you have an a value of 0, then the real part becomes invisible and you've just got what look like just imaginary numbers. So this is kind of the definitions and what everything we're doing in this lesson is based off of. This idea that the square root of negative 1, we're calling that I. Now you might be wondering, okay, that isn't really a thing. What are the real-life applications of this? Like, why do we care about imaginary numbers? And it's worth pointing out that really all numbers are imaginary to some extent. I mean, just think of the real number 2, right? I mean, when's the last time you were walking in your daily life and just saw a 2 that you could reach out and touch? 2 isn't a physical thing. It's a mental representation of something that's helpful. Imaginary numbers are just a weirder mental representation of things that are helpful. Negative numbers are a weird mental representation that can help us. But here's some real-life applications that these imaginaries actually could help with. One of those that we'll see later on in this lesson is electrical engineering, modeling what's called the impedance of an electrical circuit. Another that we won't be going into is probability distributions in quantum mechanics. And one that you might see in your mathematical studies at some point is doing rotations on a graph. It turns out imaginary numbers and their properties are really useful for this. So don't knock them just because they're imaginary, but we are going to learn how to interact with these. So for our first trick using imaginary numbers, we're going to see how we can simplify square roots of negative numbers. So we have the square root of negative 72 here. In the past, we would have said, can't do it, square root of a negative number does not exist. But we can actually go a little further using this new framework. First thing we're going to do, and I never usually do this step explicitly, but I'm going to show it to you now so you can see what's happening. When we're simplifying radicals, remember we're allowed to unmultiply the number inside, the radicand, into two different numbers if it's useful to do so. So one thing we could do here is split this up into the square root of negative 1 times the square root of 72. We can unmultiply it. And the reason this is useful is because, hey, we have a way of talking about the square root of negative 1. We just call that I. So in practice, I never really write this split in the beginning. I just take out the I right in the beginning. by taking an I outside the radical and changing the sign of the number inside. Ooh, that's kind of grisly there. But in any case, you should always do this first whenever you encounter a radical with a negative before you do anything else. And at this point, the square root of 72, that's just kind of a straightforward, plain old normal radical simplifying problem. Pause the video and see if you can take this the rest of the way. All right, so if I'm trying to split up 72 into a perfect square times something else, I've got a few options. I could break it up into a 4 or a 9, or even better, a 36. 36 times 2 is the fastest way to do this. And the square root of 36 is just 6, so that's going to go next to the I that's already out here. I can call this 6I radical 2, and now that's fully simplified. The ability to simplify square roots that have negatives inside is now going to allow us to find all the solutions for every quadratic equation, even if some of those are complex roots and have imaginary components to them. So I'm going to give you some time to try this one on your own. You're really just going to do what you would normally do, only if you end up with a negative inside a square root, well, now you have a way of handling that. Pause the video and give this one a shot. All right, so just like we always do when we're solving one of these in a situation like this, if I see that I can isolate the x squared, I'm going to try to do that and solve it by square rooting. So I can first add 11 over to the other side. That gives me negative 36 over there. And then to isolate x squared, I'll divide by 2. So I have x squared equals negative 18. And at this point, to get x by itself, I have to take the square root of both sides. Now, you did remember the plus or minus, right? That's still a thing. If you're square rooting an equation, whether or not the answers actually exist, you do need to represent that there's two of them, a positive and a negative, unless you have like the square root of 0. So now, normally, again, at this point, we would say no real solution because we're square rooting a negative. However, with imaginary numbers, we can write the complex solutions, which might be useful in some other setting. So first thing to do here, again, if you have a negative, take out the I right away. So plus or minus I radical 18. And then 18, we can split that up into 9 and 2. Square rooting that 9, we end up with plus or minus 3I radical 2. On this next problem, we want to find the complex zeros of the function. So again, we know how to find zeros from a function. Just basically do that and allow for the existence of imaginary numbers. Pause the video, give it a shot. All right, so just like before, we're going to set this thing equal to 0 and get x squared by itself in square root. So we can subtract the 20, divide by a 4, so that's negative 5 over there. And then if I square root both sides, now I've got plus or minus the square root of negative 5, which, taking out the I can call plus or minus I radical 5. So if you're doing the non-honors version of this lesson, for you then this would be the end of part 1. You can pause the video, do whatever assessment you need to do, and then you can rejoin us. The next slide is going to be an honors one. You can skip over that. If you're doing the non-honors, you would be starting up again on what I'm calling example 4. If you're doing the honors, then just let's keep going. We got one more. All right, so for this honors-only example, this one involves solving complex number equations, for lack of a better word. Here's the idea. So we have this equation with some complex numbers that equal each other, and we have to find values of x and y that make this equation true. So the easiest way to do this is to kind of just match up the real numbers and the imaginary numbers. So essentially set the real terms equal to each other and solve, and then just do the same thing for the imaginary terms. So pause the video and see if you can make that happen. All right, so our real terms, we've got 2x and 10. Now, how do I know those are real? Well, they don't have an I next to them, so that's really the only way I know. So 2x equals 10, meaning that x equals 5. And then for the imaginary parts, we have negative 7i, don't forget the negative, equals yi. And then just dividing both sides by I guess, we have y equals negative 7. So if you're doing the honors version of this lesson, this is the end of part 1 for you. You can pause the video, do what you need to do, and then come back on example 4 for the next piece. Welcome back, whether you're doing the honors or non-honors. This is the beginning of part 2. We're going to start this one off by figuring out how to simplify some expressions where we are adding and subtracting complex numbers, like this example right here. So you might actually already know how to do this. I mean, what would you do if these i's were x's, right? Using that kind of reasoning, pause the video and see if you can just get this before I show you how to do it. All right, let's see how that went. So if these were x's, I would just get rid of these parentheses. So negative 10 plus I, and this is just a plus invisible 1 being distributed, so this is just plus 8 minus 4i. And then I would combine like terms. Now when you are combining like terms, you can treat I like a variable when you're combining those. So again, it behaves just like an x in this situation. So we have negative 10 plus 8, that's negative 2. And then I plus negative 4i would be negative 3i. Because if I had x and negative 4x, that would be negative 3x, right? So this is it. This is all you had to do to simplify that one. Moving on to the next example, if we're going to show you addition, we might as well also show you some subtraction. Pause the video using kind of the same reasoning over here and see if you can get to the bottom of this one. All right, so this one was a little bit trickier because of this minus. The first parentheses we can just get rid of for free. We just have an invisible 1 being distributed there. For this next one, though, we have to distribute a negative 1 to each thing inside. So this will be a negative 2 and then minus 4i. Both of these get a negative 1. But then the rest is just the same as adding. So we have 6 minus 2 is 4, and 7i minus 4i gives us a plus 3i. So this next example is an honors topic. If you're not taking the honors, feel free to check it out. If you are taking the honors, then here we go. So we're given this circuit here, and we're being asked to find the impedance of the series circuit. And what does all of that mean? So this is one of those real-life applications of complex numbers we were talking about in the beginning. So the impedance is essentially the opposition to flow of electrical current, whether in a whole circuit or in just an individual component. And this opposition, this resistance, although resistance is actually a type of impedance along with reactance, but don't worry about that. This is essentially measured in something called ohms. All right, it's kind of like when you're meditating. Ohm. Anyway, what do all these things mean? So there's 3 different components that are in these diagrams. Those components are resistors, inductors, and capacitors. And they each have their own kind of symbol represented here, and they each have their own sort of thing you have to do with the impedance to calculate it. So for the resistor, the symbol for that is this little squiggly sort of Charlie Brown looking thing here. And the impedance for that is just going to be a real number, like a 2 or 7, like whatever the ohms is here, it's just that number. Now inductors, those are represented by this little squiggly sort of spring-looking thing. And the way we represent the impedance of those is with a positive imaginary number, which I'll call Li. The L is just a number, but you have an I next to it. The capacitors, those are these little double dash sort of deals, and those are represented using negative imaginary numbers. And I'll just put a negative C next to the I to represent that. So you might be wondering, okay, what do I actually have to do to find the impedance of a circuit like this? So it's just going to be the sum of these 3 parts. So here's a little formula you can use. I equals R plus Li minus Ci. And the R, the L, and the C are just the numbers they're giving you on the diagram here. So pause the video and see if you can actually make sense of this and figure out what you need to add together to get this impedance. All right, let's see how that went. So for the R value, we see here that the resistor, the spiky wave here, has a 5 ohms next to it. So the resistor impedance is just 5, real number 5. Next up, the inductor, the squiggly here, has 3 ohms next to it. So that's going to be the positive imaginary number 3i, and we're going to add that in there. And then finally, the capacitor has a 4 ohms next to it, so that's going to be the negative imaginary number 4, so negative 4I. And then just combining all that, we have 5 minus 1I, and that will be in ohms for the units. So the trickiest part of this is just remembering, like, of these three things, which one's the real and which one's the negative versus the positive imaginary. Once you've got that straight, it literally is just adding these three things together. For our last topic on this one, we're going to figure out how to multiply complex numbers together. So one crucial fact here is that we're going to need to figure out what happens when we raise I to a power like 2. So as kind of a basis for that, since I, remember, equals the square root of negative 1, well, if that's the case, what do you think I squared would equal? Well, if I square a square root, I just get whatever was inside. So theoretically, this should just be negative 1. And that's the definition that mathematicians are all agreeing on, is that I squared is just negative 1. Now, this is kind of weird because you're taking something that was an imaginary number and it becomes a real number. Negative 1 is a real number. You can put it on a number line. So we're going to use this fact to make sense of all the multiplying that we do from here on out. And we could do higher exponents. You can, split things up into I squared times something else. Like if you needed I to the third power, I squared times I, negative 1 times I would give you negative I, and you can keep going. We're going in a different direction. So here's our first example, multiplying complex numbers, 3I minus 5 times I plus 4. And I'll just give you a little bit of a hint here. FOIL, multiply it out like if this was x's. The only difference is that when you encounter an I squared, you can now simplify that into a negative 1, which will allow you to simplify this far more than you normally would if these were regular variables. So pause the video and see if you can follow that line of reasoning, and we'll bring it back together. All right, so foiling this out, we do firsts, outers, inners, last, basically just double distributive. 3I times I, that's going to be 3I squared. 3I times 4 gives us plus a 12I. Minus 5 times I is minus 5I, and then minus 5 times 4 gives us negative 20. Now remember, I squared is really negative 1. So instead of writing 3I squared, I can write negative 3, because I have 3 times negative 1. And then I can just simplify the rest of this. So I have negative 3 minus 20. That's going to be negative 23. And then 12I minus 5I gives me 7I. So that's my final simplified answer for this. So one thing that kind of comes out of this is because you can always simplify powers of I to either an I or a 1 or some combination there, you're never going to get anything with an exponent higher than 1 as a final answer to one of these. So now that we've done that first one, here's another example that's kind of nifty in a different way. Pause the video and let's see what this one comes out to. All right, so this one you could FOIL it out like I did here, or you might have noticed that this is kind of an A plus B, A minus B situation. So you have that A squared minus B squared shortcut. You could just square the two things and stick a minus between them. So this would end up being I squared minus 5 squared, or I squared minus 25. But wait, what's I squared? Oh yeah, it's just negative 1. So negative 1 minus 25 gives us just negative 26. So it is possible to start with a full complex number and get a real number out of it if you multiply it by this. Just to sort of plant the seeds here, when you have the same terms but opposite sign, those are called conjugates. When you multiply an imaginary or a complex number by its conjugate, you always get a real number. Kind of cool. So did I just imagine it, or is this the end of the lesson? Nope, this is a real ending. Hope you enjoyed it. Till next time, Mr. Sutton signing off.